Can somebody chat me a message telling me whether or not you hear me?
We can.
Okay, cool. Yeah, it kept saying that my speaker wasn't working. That was freaking me out. How's everybody doing? Hope we're all hopped up and ready to take our tests. Has anybody in this class started taking their test 3 yet? Victoria, have you taken it or even attempted it once?
No, sorry. I was unmuting to say no, but I was waiting if anyone was going to say yes.
Okay. I'm not sure if anybody had, but one of my students in my other class reported that there was something wrong with it. And I noticed that when I was making it, I clicked on a test bank that I had made for test 3. And in that class, it was astronomy. So students got scared and saw like 6 questions that they had no idea about. Anyways, I'm going to check it right after class today. And if that's the case, I'm going to go ahead and change it. So if you haven't taken it, don't bother until you see one that says this is the correct one in the description. Anybody have any questions?
You said don't take it?
Yeah, don't take it. Like I said, immediately after this class, I'm going to check it. And if it's right, then I'll write in there that this is the correct version. And if it's wrong, then I'll put the correct version in there and I'll write this is the correct version. So I'm thinking nobody has taken it. Is that correct? Anybody here has taken it? Okay. Well, that's good. I mean, that's good and it's bad. I wanted to make sure you guys took it once, but I pushed the deadline back to Sunday since that happened. So y'all now, instead of having till Wednesday, you have until Sunday. I would definitely recommend once you see that it is correct, and like I said, I suspected it would be done within 30 minutes after this class is over. I would take at least one attempt at it because y'all are ready for it already, especially if you've been working on the homework. And that way you'll have 1 grade in the books and you'll still have 2 more attempts to make it 100 if you want. So does anybody have any other questions unrelated to this or related to this or related to the course material so far or anything like that?
Yes, I was doing the last homework, and for one of the questions, I put in the right answer, but I put it a different way, and it was wrong. So I was just wondering if
take a screenshot of what it marked wrong, and if it tells you if it shows you the right answer at the same time, take a screenshot of that, and I'll correct it for you. That way I know which one it is and all that good stuff.
Thank you.
It does sometimes miss things. It's pretty good at telling like equivalent versions, but sometimes it doesn't. It wants you to do some extra algebra that I don't think is necessary, so that can happen. Anybody else? All right, well, we're going to go ahead and get started then. We're doing chapter 7, which is on work, okay? And what I want to try to do is motivate a definition of work to make sense and then show you that it is in some ways at least equivalent to your everyday definition of work. So I'm going to use as a model for that cutting the grass. So if you've ever cut the grass, you've actually probably figured out a little bit of physics and didn't necessarily even realize you had. But one thing I can tell you is basically work is, or a conceptual idea of work is anything that can drive a nail into anything. So what I mean by that is any force large enough to push a nail into some other surface, and that nail can be, infinitesimally thin, but be pushed into something, and that can be infinitely soft, like sour cream. Okay, if you can actually drive a nail into sour cream, then whatever caused that nail to be driven in the sour cream is work. So that's sort of the idea. So what I'm going to do is start with an idea of work that you know from everyday life. It's a pain in the butt, or it's a great deal of work to mow your grass. And if you take for instance, a push mower, and what you'll do is maybe its blade is 28 inches and you push it like this. Now, normally when you're a grown up, you can push down on the arms, or excuse me, on the handles of the mower, sort of like this, and walk along this way and it works fine. But when you're a small kid, when you first start cutting grass like I did, I wasn't tall enough to get it that high over the handles. So I ended up pushing like this. And actually what that is your body figuring out physics. Your body sort of realizes that I get the most work done when I apply a force directly parallel to the direction I want to travel. And that's going to become important because that's really how work is defined. So I think you might argue that if you have a 28-inch wide lawnmower and you go, say, north-south, so you go run to north, get to the end of your yard, turn around, move over one width of the mower, and then head south. Get to the end, turn around, move one width of the mower, and then head north again, right? Now, each one of those might be 100 feet long. And of course, if you do 300 of them, then you've gone basically about 100 yards. That's probably your total distance. And if you do enough, you actually get a mile. And in fact, if you take the total distance you walked, you can sort of see that as an indicator of how much work it is. For instance, if one yard only required you to make 100 trips back and forth, and the other yard required you to take 300 trips back and forth, you'd probably think that the trip or the 300 trip yard was about 3 times as much work. Does that make sense to everyone? If that's the case, and I think y'all would agree, even though y'all are obviously mute at this point, I think you would agree that work in everyday life should be treated somewhat as being proportional to the distance traveled. Does that seem reasonable for this particular example?
Yes.
Yeah, that seems pretty reasonable, right? Now, let's imagine another scenario in which case your fat little sibling wants to get their fat little butt and sit on the lawnmower while you're riding, while you're pushing it, right? Now you let them because you love them and him or her, and you want them to have fun, you want them to have their way, and you're also kind of happy by the fact that they don't realize the lawnmower's going to get hot, and eventually it's not going to be that comfortable. So you let the little turd sit on your lawnmower, and then you push it, right? And you quickly discover the error of your ways in that you realize, oh crap, this lawnmower is now heavier, so it's actually harder. So would y'all argue that the amount of force you have to apply is also proportional to the work, or the work is proportional to the amount of force you apply? Would y'all agree that that's the case?
Yes.
Yes. So we can come up with an idea that work is proportional to distance traveled and the force applied. I hate it when this thing gets like this and it's not like focusing. Oh, well, there you go. That was pretty good. Okay, and it's not far off. In fact, the formula is fairly correct. And if we take into account what I just told you about the young kid pushing a lawnmower and their arms going sideways, what you'll realize is when you actually apply a force, say F, to an object to push it a distance represented by the vector, say D, then you can imagine this force as being tail to tail with this other distance vector D, and that would be the same as this angle theta. Do you see that this force F can be considered to be a component of F that's parallel to the distance, F parallel, and a component that is in fact perpendicular to the distance and is F perp? Do you see that only this component is really that helpful in making the lawnmower go? Does that make sense to everyone? Another way of looking at it might be to say, imagine the force over here, and you see that F parallel is this vector right here. And you see that F perpendicular is this vector right here. And I think you could see that F times the cosine of theta would be the magnitude of F parallel. Does that make sense to everyone? So in fact, that's what your body figured out. When your body realized that I was sort of wasted motion and I decided just to push horizontally, That was because my body realized that I was getting the most bang out of my buck for my arms applying a force directly parallel to the motion. And that's the way work works. In other words, this component of force right here, it's not only wasted because it's perpendicular to the direction you want to go, but it's even worse than wasted because we learned 2 chapters ago that when you apply a force like this force can actually increase the normal force. And since the friction force is proportional to the normal force, then you're making it even worse on yourself. Okay, so we can go right now as the definition of work is equal to the force vector. And I'm going to do something neat here. I'm going to introduce a dot product dotted with the distance vector. Because with that, you may or may not cover dot product yet, also called the inner product and also called the scalar product. You might not have covered that in your pre-calc / trig course, but you can see it's force times distance. So I think you can realize that the units of work, whoa, let's work with a triple W. It's a triple woo. So the units of work is 1 Newton times a meter, which is actually defined to be 1 joule, and that's Joule. Okay, that's what the units are for work. It's called the joule. We can use the microjoule, the nanojoule, the megajoule, the kilojoule, the gigajoule, all that good stuff. But it really is just a Newton times a meter, which happens to be the same unit as we find for torque, but we don't never call it the joule when we're dealing with torque. So just keep that in mind for your future. So this is an actual formula. And in fact, 1 joule is about as much work as it takes to lift a good size, hearty, red, delicious apple from the ground to the top of a desktop or the top of a table or a dining room table or something like that. So that gives you an idea what a joule is. Not only that, if you realize that 1 watt is equal to 1 joule per second, and then you think about a 100-watt light bulb, and you can leave that sucker on for, you know, all day and all night for a month and have, if that's the only thing running, you might have a power bill of, you know, $8 or something like that. When you realize that, you're like, holy crap, electricity is really cheap, because what this is saying, a 100-watt light bulb is saying, I'm basically getting enough energy from the power company to lift 100 red delicious apples from the ground to the tabletop every second for a whole month, and it only costs me $8. So that's one way that it might make you feel better about paying your power bill, because you're getting a lot of power, or a lot of energy actually, for a small price. So that's the idea of work. And this dot product is special. I will give you the general definition of a dot product, and that is, if you have a vector A, let's say like this, and the vector B like this, and I've got them tail to tail, and you have them separated tail to tail by the smallest angle. Notice there's 2 angles here. I could go from A to B, or I could go from A to B this way, right? The smallest angle is the one that's relevant. So if I want to calculate A dot product with B, first I got to realize it's a scalar. And second, I'll give you the definition of it. And the definition of it is A magnitude times B magnitude times the cosine of the angle between them, which, by the way, can also just be written AB cosine theta. Okay. Now, how do I know this is the definition? Well, I told you I wanted to be able to find some way to find a component parallel to the distance vector. That's sort of what makes sense for us for work. So if you imagine it one way, you can say, okay, well, let's take a vector. Let's break up this vector A and do a component parallel and another component perpendicular to B. Or let's say a component of B perpendicular to A, or something like that. So in this case, if I wanted to find a component of B that is perpendicular to A, or a component of A that's perpendicular to B, then I can do stuff like this. I can make this triangle right here. Notice this triangle right here has, I'm going to do it in different colors so you can make some sense of it. This is going to be A parallel to B. And this is going to be A perpendicular to B. Does that make sense? So I think you can see that if I want the component of A parallel to B, which is also called in my notation, now different books use different notation, and maybe they've got it standardized by now, and maybe they did when I learned it, but I'm not sure it is. But if I write the projection of A onto B, then I'd write that, and it's actually a vector quantity. What I would write is I would say that A parallel to B is equal to the magnitude of A times the cosine of theta. Do you see that when since this right triangle is right here, if I take A and multiply it by a cosine, I get that part right there. Well, if I really wanted a vector, I could use this thing called the projection of A onto B. That's the way I word it. Some books might actually do the B and A in different places. But in this case, what you'd say is, I could get the magnitude just by taking the dot product. Then I'd get AB cosine theta, but I'd be too big by a factor of B. So what I want to do is divide that by B. Okay, then I just get AB cosine theta, but I also want it to be a vector because it's got the vector symbol over there. So what I really should do is make sure I get the AB cosine theta in the direction of B. So if I put B up here, well, now it's too big again by B, so I have to put B squared down here. So that is the projection. So that's a nice, neat mathematical formula that can come in handy. So if you ever want the vector that is parallel to a vector B, but it's the part of A that was parallel to B, then you can just compute this thing. So that's one of the things we can use for use the dot product for. Now, alternatively, remember I started drawing this. Well, that's because I got a little convoluted in my idea. If I really wanted to find the component of, let's say, B perpendicular to A, then I really need to do this. I mean, the component of B perpendicular to A, yeah. Then I really need to extend this vector way out here and do this. Now I see this is the component of B perpendicular to A, this guy right here. And this guy right here is the component of B parallel to A. And lo and behold, B parallel to A is just B cosine theta. Because again, you can see I got a right triangle, the angle theta. This one's adjacent to it. So I'm going to multiply cosine theta times B to get that. And lo and behold, you could say B parallel to A is equal to the projection of B onto A. And notice that's the one that appears a lot, the one in the little bottom down here. So what I'm going to do is I'm going to say A dot B, and this is the one that appears a lot. So I'm going to put another A vector here and an A squared down here, and that's it. Okay. So notice the B down here appeared there, and there. And in this case, the A appears there, and there. So that's exactly the right formula. So if you just wanted the magnitude of it, if you just want the component of A parallel to B, well, that's just A cosine theta. Similarly, if you just want to B parallel to A, that's just B cosine theta, and all that works fine. Okay. So that's why we introduced the dot product at all. And I've given you a definition of A dot B. A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta. But I want to take a break and show you a little bit more of the mathematics of a dot product. Because look at this. If I actually have what the dot product is, and I have the magnitude of A and the magnitude of B, I can use this to find the angle between the two vectors A and B. So it'd be really, really nice to find out what A dot B is without using the angle theta, because that's not normally how we're given vectors. We're not normally, especially in 3 dimensions, we're not normally given an easy way to figure out the angle between A and B when they're tail to tail, right? So let's start off by using this definition of A dot B. A dot B is equal to the magnitude of A times the magnitude of B. I don't know why I wrote C there, times the cosine of theta. So anybody want to take a guess at what I hat dot I hat would be?
That's, oh, wait.
Yeah, I think you're right.
I was just gonna say your X and your Y, but sorry,
Right.
it's
It's
not.
the X and the X, right?
Okay.
So what do y'all think? What's the magnitude of I hat? Anybody, what kind of vector is this called? Starts with the letter U.
Unit vector?
The unit vector. And anybody recall what the length of a unit vector is?
One unit?
Yep. Notice it's exactly 1 unit. It's not 1 meter, not 1 inch, not 1 Newton. It's just 1. Okay. The other one also has a magnitude of 1 because they're the same, right? And what's the angle between them when they're tail to tail?
180 degrees?
Actually, it's exactly 0 because if it was 180, they'd point in opposite directions. But I hat and I hat both point in the positive X direction. But I think I get what you were trying to say there. So yeah. So when you do I hat dot I hat, you're going to get 1 times 1 times 1, which is just 1. Would you believe me if I told you that J hat dot J hat gives you the same thing? Does that make sense?
Y is, oh, okay, because they're both 1.
They're both 1 and they're parallel, so the angle between them is 0. And what about K hat dot K hat? They're in the Z direction.
1 as well?
1 as well, exactly. Now we're going to get a little fancy. Let's do I hat dot J hat. Ooh, we still get 1 times 1, right? But now what's the angle between them?
Is it 90?
90 degrees. And everybody knows what the cosine of 90 is, don't you?
0.
0. And you can probably guess from the symmetry of it what J dot I hat is. Zero, right? And how about I hat dot K hat, which obviously is equal to K hat dot I hat?
0 again?
Uh-huh. And finally, what about J hat dot K hat, which is the same as K hat dot J hat? So that's a general rule. The dot products, the order doesn't matter. So J hat dot K hat versus K hat dot J hat. What do y'all think that is?
Still 0?
Still 0. Yeah, and in general, like if you take a linear algebra course, they will call I hat just E1 hat, and J hat, they'll often call it E2 hat, and it actually can be used for any basis. I'm just using it for the Cartesian coordinates right now. And K hat would be E3 hat. So that's another terminology to use. The reason why is I want to show you this neat little rule. There exists this thing called the Kronecker delta function, which is really just a matrix. And the matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. And we normally write it IJ like that inside of a bracket. And in fact, now that you have that, it makes perfect sense that EI dot EJ, not to be confused with the I hat and J hat before, just using indices, is equal to delta IJ. Or let's try it with a different one. Let's say EM dotted with E n is equal to delta M n. So you see, the only time this was 1 was when it was 1, 1, 2, 2, or 3, 3. Any other time it's 0. That's all they're saying. So this is basically all 6 of those facts, 1, 2, 3, 4, 5, 6, actually all 7, 8, 9 of them really. That's all of those facts combined into one. So now that we know that, we're in a position to come up with another version of the dot product, another definition of the dot product that will help us get the dot product without knowing the angle between the vectors. And in fact, you don't even have to have the magnitude of the individual vectors, but you can, and it will help you to find the actual angle between them. So let's look at what that is. I'm going to do this one in blue so we can change the page a little bit. So let's say A dot B is really going to be equal to AX I hat plus AY J hat plus AZ K hat. And then I'm going to dot that with B, which we're going to call BX I hat plus BY J hat plus BZ K hat. Well, the neat thing about a dot product is it's part of an algebra, so it defines, or it has the same rules that we know from algebra, like the distributive property, the commutative property, and all that stuff. So when I want to actually multiply this one, I have to use the distributive property, which says this guy has to multiply by each one of those 3, and then this guy has to multiply by each one of those 3, and then this guy has to multiply by each one of those 3. But the multiplication is actually a dot product. The other neat thing is the dot product is what we call a linear operator. Or it's a linear operation. And what I mean by that is if you do some constant C times V dotted with some constant D times A, then that's exactly the same as C times D times V dot A. And actually, it's also true if you do C V plus DA dotted with, let's say, EQ plus F X vector. So in other words, you do the distributive property. So I get C and E in front of V dot Q, and then I get C and F in front of V dot X, so on and so forth. So that's really what we mean by linearity. So when I do AX I hat dotted with BX I hat, I get AX BX I hat dot I hat. Now when I do the first with the second, I get AXBY I hat dot J hat. And when I do the first with the third, I get AXBZ I hat dot K hat. Now I'm going to do the second with the first, and I'm going to get AYBX J hat dot I hat. Now I'm going to do the second with the second, and I'll get AYBY J hat dot J hat. And now I'm going to do the second with the third, and I'll get AYBZ J hat dot K hat. And then finally, I'm going to do the third with the first, second, third. So the third with the first would be AZBX. And that, of course, is K hat dot I hat plus AZBY K hat dot J hat. And then finally, AZBZ K hat dot K hat. Now, what that tells us is because we know I hat dot J hat, or I sub M versus, or E sub M versus E sub N, is only 1 when the M is equal to N. So that means this guy is going to be 1 this guy is going to be 1, and this guy is going to be 1, but all the other ones are going to be 0. So now we've got a whole new formula that is A dot B is equal to A sub X, B sub X plus A sub Y, B sub Y plus A sub Z, B sub Z. And we still have the old version, which is A, B cosine theta, which I could also call A parallel times B, or I could also call B parallel times A. So that's all the different versions of definitions of the dot product. So hopefully y'all seen that already in your pre-calculus class, or the trig part of your pre-calculus class, or perhaps in high school. But that's what a dot product is. And it just allows us, with a little bit of manipulation, remember this projection thing I mentioned, with a little bit of manipulation, you can actually quickly determine the component of a vector parallel to another. So for instance, if you wanted to know what fraction of the light coming through your windshield is going to actually go to, say, lighting up the dashboard immediately under it, then you take a dot product of the angle of the sun with the perpendicular to the windshield. That's a common way of dealing it. Or if you want to know what fraction of the sunlight is going to hit, say, a solar panel, again, you can use a dot product. On a microscopic level, it turns out that atoms align themselves in neat little patterns when they make molecules or when they make solid materials. So sometimes you'll have, for instance, sort of like a die, only it's slightly different because it's basically 4 atoms making a square in the back, 4 atoms making a square in the front, but then 1 atom dead center in the middle of the cube. So when you're confronted with experiments that show you the positions of the atoms in, say, a lattice, in, for instance, a chunk of aluminum or a chunk of sodium chloride or something like that, you can actually use the dot product to find, say, the angle between this bond and this bond. Because as long as you know how to calculate this part, then you can easily calculate A and B and solve for theta. Notice that's even in 3 dimensions, so that's pretty impressive. So let's try a baby example and see if that really works, and then I'll try even more of a baby example. So for instance, we might have, let's say, the vector 4, 3, 5, and that's going to be vector A. And now I'm going to take the vector that is 1 square root of 3 and 2, and that's going to be vector B. Okay, so y'all know the 3, 4, 5 triangle. Anybody remember what this angle is for the 3, 4, 5? Take the inverse tangent of 3/4. So I'll do 0.75 trig. I'll do trig inverse tangent 0.75, and you'll get to 36.9 degrees. So we expect this one to be 36.9 degrees, right? What about this one? It's 1 down here, it's square root of 3 here, and 2 there. That's our 30, 60, 90 triangle, right? So we expect this one to be 60 degrees. So we bet theta is going to be equal to 60 minus 40 would be 20. And then 40 minus 27, or excuse me, 40 minus 37 would be 3. So I'm going to say 23.1 approximately. Well, we know the vectors and their components, so let's check it out. A dot B is just going to be A sub X, which is 4, times B sub X, which is 1, plus A sub Y, which is 3, plus B sub Y, which is the square root of 3, plus 0, because there's no Z components either there. Well, that's all equal to the magnitude of A, which we see as 5, times the magnitude of B, which is 2, times the cosine of the angle between them. So I get 4 plus 3 root 3 is equal to 10 cosine theta. So theta is supposed to be equal to the cosine inverse of 4 plus 3 root 3 over 10. That's crazy, right? Well, let's calculate it. So I'm going to do 4 plus 3 times the square root of 3. And I'm going to divide that by 10. And I'm going to take the cosine inverse. So I'll do cosine inverse of, now I'm going to take the answer I just calculated. And look what I got, 23.13, which is exactly what we bet. Isn't that cool? Now that doesn't seem that useful, because obviously you can just do the subtraction we did. But trust me, when you're dealing with vectors in 3 dimensions, that's a nightmare, right? Figuring out that angle, which is along the XY axis, and this one, which has a X, Y, and Z component, that's an entirely different beast. So that's one of the usefulnesses of the vector product, or excuse me, the scalar product. I want to show you another usefulness now, and this one's a lot more, to me, important. I'm going to ask you all a question, and by chat, I would like you to tell me by typing, yeah, yes, you have, or no, you haven't. Yeah, 36.9. Thanks, Jared. How often do you use your law of cosines? If you use it a lot, type yes. If you don't use it a lot, type no. I just want to get an idea for this. I know I have a poll thing I could do here. I didn't make it up though. So we got Victoria uses it a little bit, or she was answering yes earlier. I suspect a lot of people don't use it, and I suspect the same reason they don't use it is the same reason that I didn't use it for a long time. And then I made sense of the dot product, and yeah, not really. Yeah, we always would try to, yes, for statics, you can use it. Yes, absolutely. I suspect most of you add vectors without using the law of cosines. We just break them down at any vector setup that we have that makes a shape other than the right triangle. We just break it up into 2 triangles. And the reason I always did it is because I never knew what the crap angle they were talking about with the law of cosines. So what I'm going to do is I'm going to show you a neat way that will help you remember it, and it'll make even more sense of the dot product. So let's imagine this is vector A. What's that now?
I put yes because I have to use it a lot in MATLAB.
Right.
I mean, later, I mean, is there like a different way? I mean, if you could tell me later, is like a different way to put that like differently in MATLAB, or? Yeah,
I will show you. In fact, this will help you, and you're just a trig identity from the usual version that they give you.
Okay.
So it'll help you a lot, I think. Let's imagine that we're going to add 2 vectors, A and B. And since they're tail to tail, we have to use our parallelogram method. And what we do is we complete the parallelogram, and then we draw a vector from the common tail to the opposite corner. and that is C vector, which is equal to A plus B. Okay, so this is kind of nice. What I'm going to do is I'm going to compute C dot C. Well, C is equal to A plus B, and I'm going to convert that to dot product it with itself. So C dot C gives me C dot C, and then A plus B dotted with A plus B is going to give me something else. Well, we know A dot B is supposed to be A times B times the cosine of the angle between them. So for C dot C, that's just C times cosine of 0, which is 1. So that one's just C squared. So you can automatically see where part of the law of cosines comes from. Also, when you do first, you get A dot A, which is just A squared, right? Just like this is just C squared. And when you do lasts, you get B squared, or excuse me, B squared. I'll take off that vector symbol. I'll also take out that little dot if I can. Okay, that dot's gonna stay there. So that's where part of it comes from. Now the other part is B dot A plus A dot B. Which we already learned that the order of the dot product doesn't matter. So I can write this as C squared is equal to A squared plus B squared plus 2AB cosine theta. Now, if you remember the law of cosines, I think normally has a negative there, and I can never remember what the angle is. But since you started off with this, you know automatically what that angle is. That angle is the angle between their common bases. So that's the angle theta. So this is the equivalent of the law of cosines. Only in this version, you know exactly what theta is. And then, like I said, if you want to get the negative sign, you can relate this to theta and 90 minus theta and all that good stuff. Because I think normally, and this is exactly why I don't use the law of cosines in its strict form. I want to say the angle that they normally refer to as this one, but it might be this one. In other words, I still don't know because I don't care. That's the stupid way. This way, I understood the derivation of it. So now I never forget. I can always use this formula right here for my law of cosines, and I will always, always, always get the right answer. Does that make sense? So hopefully that will help you. Now let's actually solve some typical problems using work. So for instance, let's imagine pulling a box across the floor. So let's say we have a box, and let's say its mass is 50.0 kilograms. Okay. And that's the line horizontal, as is the floor. Okay. And let's say I'm pulling up on it at an angle of about 37 degrees with a force of, let's say, 200 newtons. I'll put a dot at the end so we can assume we're going to use 3 sig figs. So what is the work being done when I move it a distance of d equals 100.0 meters? Okay, so in this case, I'm moving it ever so slowly, and then I come to a stop, and it was at rest, and it ends up at rest, and I want to know what is the work done. Well, work is just equal to F dot D, which in this form, it's easier to just say F parallel to D. And we see that we have a 37 degree there, which should make you think that's really close to that special 3-4-5 triangle we did before. Remember the 3-4-5 was 36.9. So if we had 36.9, which is pretty darn close to 37, then this would be 3, or excuse me, this would be 4. this would be 3, and this would be 5, right? But since the 5 is 200, I'd have to multiply this by 20 to get 100. So I have to multiply it by 40 to get 200. Well, I'd have to multiply this by 40 as well, and this by 40 as well. So that is my component that's actually parallel. So I know it's going to be 4 times 40 be 160 newtons times 100 meters. And I get 1.60 times 10 to the 1, 2, 3, 4 joules. Okay. So that's about as much work as required to lift 16,000 red delicious apples from the floor to the top of the table. So does that make sense? See how I just applied the idea of the component of F parallel? All I had to do was take F and multiply it by the cosine of 37. Well, cosine of 37 is about equal to 4 over 5. So basically I was going to take the number 200 divided by 5, which gives me 40, and then multiply that by 4, which gives me 4 times 40, which is exactly what I ended up doing. Okay, but I'm doing it using this because I know a lot of people are going to take statics next, or are currently taking it, and I know a lot of statics, they do this with these special triangles as opposed to you know, weird angles where you have to use your calculator. Any questions on that? So let's say we're going to carry something up a hill and we want to calculate the work done. So let's say we've got a package right here we're carrying. Let's say this is 25 kilograms. And I'm holding it like this. Okay. And I'm going to walk it up this hill. I'm evidently goose stepping or something. I don't know what happened there. Maybe I stepped in some poop and I'm trying to shake it off my foot. I don't know. Anyways, I'm going to bring it up here. And the net result is that I'm going to have walked it up to this height along this particular path. Right? And let's call this height equal to 10.0 meters. If I do that, then I might want to know several different types of work. So let's see, I want to see the work done by me. I would like to see the work done by gravity. And let's say, yeah, we're gonna let's say the network, W net, and that's the total work done on the box. So what we're doing here is we're going to have to basically figure out what is the work done by me in carrying this block up 10 pounds. Now, in principle, I could say, you know, find out what this angle is and all this good stuff. But really, we don't necessarily need to do that as much as you might think, because really the only thing that matters is the component of force parallel to the distance. So really all I got to do is I got to provide enough force to calculate the force acting on it, which is a force due to gravity, which acts downward. So if I take the summation of forces in the y direction equals mass times acceleration in the y direction, and I assume that I'm not really going to appreciably speed it up. In other words, I'm going to slowly walk it up here, like so. So yeah, it might gain a little bit of speed here and there, but it's really not going to do much. Then I can just say, well, this will allow my minimum force. Well, the minimum force is the force by me minus mg So the minimum force is the force that I can do in this scenario with no acceleration. So I see that the force done by me is actually equal in magnitude to mg. Does that make sense to everyone? So yeah, the D vector really is this guy right here. And you might think, well, I can't even solve this because they didn't give me the distance traveled, but they didn't really have to. The reason why is because work for part A is just F dot D. So really, in this case, I'm not doing F parallel to D. I'm doing, in some sense, F with D parallel to it. So the component of D parallel to F is in fact H. And in fact, they're anti-parallel because H is going up and the force I'm applying is actually going up. But when we do gravity, the force of gravity will be going down. So they'd be anti-parallel. So in this case, I'm going to say this is just going to be equal to 25.0 kilograms times 9.80 meters per second every second. That's from this times D parallel, which is 10.0 meters. So when I do that, I do 25 times 9.8. And that, of course, gives me 245 times 10. And that gives me 2,450. So that's the force, or excuse me, that's the work done by me. Does that make sense? Now for part B, I want to know the work done by gravity. Well, the work done by gravity is F gravity dotted with D. But again, I could just use the component of D parallel, or in this case, anti-parallel. I could use FG times D times the cosine of the angle between them. So in this case, I'm going to say the force due to gravity, which is that M times G again, only it's pointing down. So that's still 245 newtons for mg. And then in some sense, I'm going to do D, but instead, I'm really going to do D times the cosine of 180. So I could say 10 meters times the cosine of 180, because D is technically pointing up, and this 180 gets me the vector pointing down. So now I can see in this case it's negative 2.45 times 10 to the third joules. Now in this case, finally, part C, work net is equal to 2.45 times 10 to the third joules plus negative 2.45 times 10 to the third joules, which equals 0 joules. Now we'll find out later that that's actually the work energy theorem. That's the reason that we actually got 0, because by me assuming that I really got no real velocity, when I got to the top, I had 0 speed. So my change in kinetic energy is 0. And in fact, the work energy theorem says that the total work done on any object, meaning done by me, by gravity, by air resistance, everything, that total work done will be equal to my change in kinetic energy. And since my kinetic energy went from 0 to 0, then the total work should be 0. Any questions on that? Now you might want to think, does the force of gravity do any work on the moon? So this is another example. Or, let's say you got the sun here and you've got the earth way out here. And we'll just assume for ease of calculation, because I told you that really it's so close to a circle, you couldn't tell the difference. At this point right here, we know the velocity of the Earth is that way. And the force of gravity, of course, is this way. Right? So this is the force due to gravity. And in fact, you might say, well, can it actually do any work? Well, in some sense, it does no work because it's always going to remain this force, this gravitational force is always going to remain perpendicular to the path. But the key point to understand here is that this was the velocity's direction it was going. And now it went this way. So by changing that, you can see that there is, in some sense, a little bit of work to be done, but it's sort of like it's doing it after the fact. Like this instantaneous force is going to make this velocity change from this direction to this direction. Therefore, it had a component that was at least somewhat parallel to this, but that only happened after the fact. But the sort of rule is basically a force perpendicular to a D is going to cause work equal to 0. So one of the magical things that's kind of neat about the force of the magnetic field is the magnetic field force is equal to QV cross B. And that cross is that other vector product, that other product of vectors that I was telling you about. In fact, there's multiple ones. There's an inner product, there's an outer product. We just did the dot product. Which is A dot B. That's also called the scalar product. And it's also called the inner product. But there happens to be another one called the vector product, and that's a cross product. So they call it the cross product or the vector product. And what it does is it actually spits out a vector. That's why they call it a vector product. But the vector is in fact perpendicular to both the vectors that you put in. So if I put in QV as one vector and B as another vector, the force is going to be a third vector perpendicular to both of those. And then in that case, you have a force that's perpendicular to the path. So again, you get no work. So it's often said that a magnetic field can do no work on an object. And that's what they're getting at here. So I definitely recommend you read conceptual example 7.3. I think it's 7-3. Yeah, 7-3. So they'll give you a little bit more explanation of that. Any questions on this stuff so far? And I'm just giving you a hint of what's to come and then telling you some other names so you'll know it. I've already posted the video from this morning's class where it does this dot product stuff again, but I didn't get far enough to do any of these other examples other than examples of the dot product. So this might not, the video today might not be posted until tomorrow. But at least you have that already to look at the dot product if you want. So if you have any questions, now's a good time to ask about those. Nothing? All right, well, we'll go to the next part then. So the next thing I would like to show to you is really what happens when the work equals F dot D doesn't really work. So work does not equal F dot D. Whoa. F dot D if F changes along D. In other words, let's imagine you're pushing an object and say along the x-axis, but at some points the force is really large and other points is really small. In fact, making a plot of F versus X, you get some craziness like that. Well, that means that this little x, let's call it x sub I, the force is f sub I. And it sort of has to be, maybe it's perpendicular to the path, maybe it's parallel to the path, maybe it has some small angle theta with respect to the path. The important thing is that it's actually a little bit different. And because, for instance, when you go to over here, you get a different, let's say f sub j for x sub j. Well, when that happens, you've got to account for that. So you're going to discretize. In other words, you're going to take the path of travel and make it into very small, discrete little elements. Okay. And then instead of just doing a dot product, you're going to have to take each little part and say f1 dot d1 plus f2 dot d2. But you're going to have to take the limit as there becomes an infinity of them. And then you're going to have to sum all those up. And of course, when you're thinking of breaking things up into smaller pieces and then summing them up, you're thinking of an integral. And in fact, work is equal to the integral of f dot dl, say. Technically speaking, this is a line integral. We don't have to do too much to differentiate it from any other integral. But I will teach you what a line integral is because we'll be using it a lot this semester and next semester. All it really means is you've got to account for, in this integral, you've got to account for the path of travel that you're taking, as well as the direction you're traveling. And that can either be done by using your range of integration to say I'm going to go from x equals 0 to x equals 3, or I can use my differential line segment to point in the direction that I'm going, say left to right. But whichever one I choose, I got to stick to that one, and the other one just becomes the positive coordinate direction. So that's the only sort of aspect that you got to worry about right now, as far as making it a dot product, making this dot product into a line integral. But that's the more robust formula for work, and that's what you have to use whenever f changes along the path. So this is the more general definition, and it does have a dot product in it, so it starts to get scary, but that's actually the norm. We're going to have a lot of stuff, especially in the second semester, where not only will you have a dot product in the integral, you'll have a circle on the integral, you'll have a dot product, or you'll have a circle with a cross product in there and all sorts of crazy stuff. So don't get scared, just piecewise follow how I teach you to do it and you'll be fine. So one example might be, I think I got plenty of time. Yeah. One example might be, for instance, the force that a spring applies to a mass. It turns out, according to Hooke's law, so remember when I told you about one of Isaac Newton's nemesis was a guy by the name of Hooke? That's the Hooke, okay? So Robert Hooke has Hooke's law, and basically what we say is that when you're compressing an object, let's say pretend like this is a beam or a 2x4 or something like that in a construction project, okay? If you put a piling up vertically, say like this to hold up a bridge, and then I look at it from the side, when you put the weight on the bridge, the weight of the bridge on the piling, it compresses it. It applies a force this way, and then the earth, of course, applies enough force this way so that it actually squishes the beam, or the piling in this case. And the piling is going to actually be compressed a little bit. And what Hooke said is the amount of deformation or crushing of this piling is directly proportional to the force applied. And it didn't have to be that way. It could be proportional to the square of the distance that it squished, all sorts of stuff. But the main thing is he found it was proportional. And as long as you don't go beyond its limit, because if you compress something too far, then it just gives way. Or if you stretch something too hard, like a spring, then it gets sprung permanently. So those are the extremes that you want to avoid. When you go to implement this in terms of a spring, though, it becomes F is equal to negative kx. And what we mean by that is you can imagine drawing an x coordinate system or x axis. Let's say this is x. And let's say there's a wall right here. And there's a spring of spring constant K, okay? And I'm gonna say this right here is at position x equals 0, Now, if I stretch the spring till it goes out to here, right? Well, the force that the spring applies to pulling object points to the left. So I'm pulling this way. The spring's actually pulling this way. So my X got more positive, and to account for that, the force had to point in the negative direction. That's why Hooke's law has a negative in it. But if you want to calculate the work done by stretching a spring, then it's just F equals KX. So for instance, if you want to know the work done stretching, so that's the work done by the force, not by the spring. What we're going to do is say work is equal to the integral of kx dx from x equals 0 to say x1. Okay, and I think that's a pretty easy integral for you guys. K is called the spring constant. In fact, K has units of newtons per meter. So when I take the integral of kx, that just becomes k times the integral of x, which is 1/2 kx squared evaluated from x equals 0 to x1. So it's just 1/2 kx1 squared. So that's our formula that we can use to find out the work done in stretching a spring by an amount x. If you stretch a spring by an amount x, the work done will be 1/2 kx squared. Does that make sense? So this is an equation that your book has numbered and therefore can be on your equation sheet for your midterm and all that good stuff. Which, by the way, the midterm is on the 13th. So we should start getting ready for that. In reality, what you're doing here to show you the line integralness of this, let me turn back and show you what's really going on. What we have is work is equal to the integral of the force stretching the spring. Now, the force stretching the spring is pulling that way. And of course, it's got to be enough to stretch the spring, which according to Hooke's law has to be K times X. So it's going to be K times X, but it's pointing in the I hat direction. Now, this is the point where you've got to choose, hey, I'm doing a line integral, so I got to choose, am I going to let my DX, my DL point in the direction that I'm going? Because it's, remember, work equals the integral of F. Wow, y'all can't see that at all, probably. My pen just acted like it started dying. Work equals the integral of F dot DL is what we're using, right? So do I let the direction of DL dictate which way I'm going? I'm going from x equals 0 to x equals x1, say, or do I let the range of integration do it? Well, in this case, it sort of doesn't matter because both are the same. So if I say I'm going to let DL choose it, then I'll put positive dx in the I hat direction. And then I'll automatically go from low coordinate to high x. Okay. Because used this to show direction. The danger is if I had went this way, I might have choose negative dx here, but I'd still have to go, since I chose this to choose the direction, then I go from 0 to well, actually I go from -3 to 0 if the distance was -3. but in this case, they're both positive, so it doesn't matter because they're both going to be in the positive direction anyways. So low x, which equals 0, and high x, which equals x1. So really what happened is, again, the linearity of the dot product means the kx dx can come out in front, and I get integral kx dx I hat dot I hat, but I hat dot I hat is just 1, and that means 0 to x1. So I still get 1/2 k x1 squared. So that's really what the line integral process was. If we, did some complex path where I went to the right and then hung a left and then went like this, then I have to break up each of those little parts, and then my DL vector would point parallel to each of those little paths, and I might even have to make up a parametric equation for the path I'm choosing, all sorts of neat stuff like that. But we don't have to deal with that kind of junk for some time. Does that make sense to everyone? All right, so that is really the more formal definition of work. Now I'm going to talk to you about the work energy theorem. So the work energy principle, or the work energy theorem, basically you can take Newton's second law of motion, and from Newton's second law, we know the summation of the forces is equal to mass times acceleration, right? We also know that acceleration is equal to dv over dt. So if I just reduce it to one dimension for right now, just for ease, I can say the summation of the forces in the x direction equals m dv dt. Okay. Now, if I imagine multiplying both sides by, let's say, dx, then I'd get the summation of the forces in the x direction dx, and we'll maybe even call it a dot product, so we could imagine that we originally had a full vector summation of forces, and when I took the dot product, that got me into only the x direction, and then that's going to be equal to m dv dt dx. Okay, so we could do something like that, or dl, or whatever we wanted to do. Yeah, let's make it dl just for the heck of it, just since I'd done the force or the work in terms of dl before. So I've got that right now. What I could do now is realize that this is the net force, therefore this whole side is the net work. Does that make sense to everybody? Since I did the total force of the sum of all the forces acting on it and dotted it with dl, that's the net work. So what I found is that W net is equal to, now get this, I'm going to say, flip this dl with this dv, and I'm going to say m dl over dt times dv, but dl over dt is just v, so I've got m v dv. So I'll say work net is equal to mv, well, actually I should say d work net, but that's not really a rule, a way that you can do it. So now I've got sort of this differential work element, W net. Remember, I didn't integrate it yet. It's just the net force times dl. So now when I integrate it, I get the integral of dw net, which I should really separate it by calling it like dw or something, but anyways, is equal to the integral of mv dv. Well, what that actually gives me, that's how I'm differentiating it from that pre-integrated version. The net work is actually equal to 1/2 mv squared evaluated from v initial to v final. So what that means is the work energy theorem says that the total work is equal to the change in kinetic energy, because we define kinetic energy to be 1/2 mass times velocity squared. Okay, So that's the work energy theorem. And it basically says the total work done to any system is going to be equal to the change in kinetic energy. So for instance, you were here with me Thursday at almost 7 p.m. Or excuse me, Wednesday at almost 7 p.m. And you more than likely had zero velocity because you were sitting at a desk somewhere. And now you are sitting at a desk, and in the intervening period, you've done work against the world, therefore the world's done work against you. The force of gravity has been pulling down on you. Your leg muscles have been pushing your body up, all sorts of stuff. You got out of bed, you got into bed, you worked, all this stuff. I can tell you definitively that the work done on you since you were with me last time is zero, because our kinetic energy has not changed. Your kinetic energy final, which is right now, is zero. Your kinetic energy Wednesday was zero. So it's zero then as well. So 0 minus 0 gives me 0. So I can tell that the net work done on you in the last, several days is in fact 0. And that's it. That's enough for this first introduction to chapter 7. We will finish up chapter 7 next time with a few more examples. You guys are free to go, but you're also welcome to ask me questions and stick around.
Thank you. See you Wednesday.
Thank you. See you Wednesday.
I was hoping to get some more information about the format of the midterm and what sort of resources we're able to use as far as equation sheets and that sort of thing.
Okay, so what I allow my students is I allow you an equation sheet, and the rule with that is that your equation sheet can only use equations that I specifically told you could use, which I've boxed them off, or equations from your textbook that have parenthesis 1-3.2 or something like that. In other words, the equations that your book wants you to memorize or keep current with are the ones that they've labeled. So like I'm looking right now at the work energy theorem, and it's labeled with a left parenthesis 7-11 and then right parenthesis. That means it's an equation that you can put on your equation sheet.
Okay, so we each can make our own equation sheet for this.
Yes. And what you're going to do is during the test, you're having a lockdown browser. I'm going to put that practice test up probably today or tomorrow, but you'll have a lockdown browser that there'll be two versions of the practice test. One of them is the respondus that you need to take once just to make sure you can get your browser to work with respondus. And you're going to get on there and you're going to have to, show me your ID with your face so I can compare the ID with the actual face I'm seeing. You can cover up the critical number if you need to. I just need to see your name and your name as it's in your roll sheet here. And I need to see your face along with the photo ID's face. And then you're going to show it each sheet of paper you have. You'll take the camera and shine it all over your work area so you can show me exactly what's within arm's reach of you or whatnot. And then you'll show me your equation sheets front and back. And that way I can verify whether you only had equations that were labeled. You're also allowed any constants that are in the front cover of the book or in the appendix of the book, tables of integrals, all that stuff is allowed. You can make copies of the tables from the front of the book if you want. All that stuff's fair game. Usually the way the tests work is they almost always give you the constants you need, except for like G, the big G for gravity. They don't necessarily give you that in the problem. They don't necessarily give you G equals 9.80. Little stuff like that they don't give you, but so if you make a copy of that inside the front cover, that's fine. And then you just take it, and basically it has rules like you're supposed to keep your eyes not look a lot like this. It'll actually ping that. They've got people that watch, and if it looks like you're doing a lot of work below your desk, they think that's funny, so they'll report it, and then I got to go back and watch it, and either I'll make you retake it again at a proctoring center or something like that. So just try not to do something that looks really suspicious. Okay, you can't have your phone with you. You have to have a scientific calculator, and you can't use your phone as that scientific calculator. It might do you well to have a ruler if you need, pencil, paper. Sometimes my tests will require you within 15 minutes to email me the work done. So you quickly take a photograph of your worksheets and then email that to me within 15 minutes of submitting your test grade, that sort of thing. But I don't always do that. So if you don't see me specifically ask for it, that means you don't have to do it. Does that make sense?
Yeah, it does. So there's going to be a practice test so that we can understand what sort of questions are on this, what
Yeah,
information.
there'll actually be two of them. One you got to take once because that'll be a respondus practice test. And then there's one that you can take a bunch of times. You don't want to take that respondus one a bunch of times. You only want to take it once to make sure your browser works and you download whatever you need to.
Okay, and do you generally provide some sort of like list of concepts or study guide, or it's just everything? Because
This
mostly my
practice test is
question,
what I do. It's just because I use basically the same bank. I have the freedom of changing 20% of the points to some questions that you haven't seen or haven't had the chance to see in the practice test. So that's what I do in lieu of like a study guide or something. You just take the practice test as many times as you can. And I mean, you could even just go back and take the old practice test for test 1, 2, and 3 or whatever, and that would be sufficient. But I actually make it even more fine-tuned than that and give you an actual practice test that you can practice with the guarantee that about 80% of the points will come from questions in those practice tests.
okay, as the books have some of those like optional sections marked with the asterisk, and my understanding was that we didn't cover a lot of those, and there was one about drag that I don't think we ever discussed in class, but it popped up on the most recent practice test.
Yeah,
you
I
have any
did do one
recommendations
problem
there?
with drag. I did that on my YouTube channel. Or actually, I did it in I think 2 of my classes, but I posted on my YouTube channel. I'd say that's fair game, but I hardly ever put that on the midterm. So I'd say you probably could bypass that for the midterm.
Okay,
You're
Got it.
saying the
And
drag.
remember, you only get one attempt on this, but you got an unlimited amount of time because the browser is locked down on your computer. That way I know you're not looking stuff up. You have shown the computer all the sheets you have at your disposal, so you don't have your notebook there and stuff like that. Because of that tighter constraint, you're basically allowed about 2 hours and 15 minutes.
okay, great. Thank you. I appreciate the information, so
No
I know what
problem.
to prepare for.
Yeah, don't stress. I mean, I want you to take it seriously. If you're not doing well in the practice tests, the practice midterms, and then yeah, you've got something to worry about. But if you can consistently get an 80 or higher for maybe 3 or 4 practice tests in a row, then you're probably in a good spot. Anybody else have any questions? Don't forget, I'm going to go ahead and check your test 3 now, which I did push the due date back. If you just don't try to take it within the next 20-30 minutes, but after that, if you see it, it should say this is the correct one or something like that in bold red. If you don't see that, then you know it's not ready yet. So y'all have a good one, folks. I'm going to go ahead and leave unless someone chats and says they have a question.
Were you able to get my emails? I sent you a couple of emails.
Yeah, I saw you come across, but actually I didn't see them all until this morning. Let me double check, make sure I got a couple from you, because I remembered your first name. On all accounts, no wonder I wasn't seeing it immediately. Yeah, here you go. Yeah, Mario, yeah, I got this. Oh yeah, the Canvas messages, I don't know where the crap they go. I don't see them.
Yeah.
Yeah, I understand, but I'm sorry about that. I got you. Yes, I can do that for you.
Okay.
Do you need to take a extra week to try to hit that midterm?
Yeah, I took this. When is the due date? I know test 3 is Wednesday or Sunday now.
Yeah, the test 3 is due Sunday. If you can get that, I think you're in a pretty good spot to take the midterm on Wednesday, or excuse me, on the 13th. Just let me know if you think you need an extension on the test, and then if you think you need an extension on the midterm, I might go to work with you. Okay.
Okay.
I'll just have to make a new test because it's, that's the reason why I make everybody take it at the same time, and so no one can tell someone else what's on it.
Okay. Yeah, I should be fine. I took this. I was able to take this week off from work, so I'm gonna try to catch up this week.
All right. I'm sorry you ran into misfortune.
Yeah, I appreciate it. Thank you.
No problem. You have a good one, Mario. Good luck with you.